skew in this place. If it is like this, yeah, of course, it's not that good. Yeah. Well, actually, even that it is skew, at least, yeah, you have still one element. This, yeah. The worst, of course, yeah, skew like this, yeah, totally like this. Or the other one, this, yeah, skew. Yeah. So it means the height itself, yeah, the height itself is the n. So the height is n. Yeah. The height is n. Okay. So the thing is, it's like type of PSD, the FL3, but able to do self-rebalance. So can all the time can rebalance. Yeah. This is, of course, is totally balanced. Yeah. If you have only one, of course, is balanced. If you have a 3-node, yeah, this also totally balanced. Yeah. Because left and right exactly the same. If you have again, yeah, F7 node, yeah, of course also totally the same because L, yeah, equal to right. So it is totally balanced tree, yeah, in binary search tree. But in FL3, actually the requirement is not strict like this. Yeah, so it should be totally the same. For each node, the height difference between the left and right branches at most 1. So this, yeah, it is, of course, it's also balanced. This is also balanced. Yeah. But this also okay. Yeah. For instance, this, so this, okay. Because the height it is, yeah, 1, and then this is 2. So the difference is 1. So okay. So the height difference between the left and right is at most 1. This is the only requirement. Not no need to be totally the same. Yeah, but if the height difference is 1, is okay. Insertion and deletion in AVL generally is allowed. And of course, you cannot all the time have the same tree. Yeah? You either insert, for instance, here. You insert here, for instance, yeah. This. Yeah. Yeah, insert this. Or you delete. Yeah. For instance, you delete this again. Yeah. You delete this. Go back to have this tree. Yeah. Go back this. Yeah. So it is allowed. But if you do insertion and deletion, so it causes the height imbalance property above. So become imbalance. I mean the height difference between the left and right branches, no, maybe more than 1, yeah, maybe more than 1. 1 here can be +1 or -1. It depends what is the perception. For instance, if this, yeah, if I said right minus L, so right, this is 1, yeah, this is 1, and then left, it is 0, right? So it is +1 then, +1. But if it is like this, so it is 0, yeah, right. It is right minus L, yeah, and then -1 here, it is become -1. So depend on the perspective, yeah, +1 or -1. Okay, but it doesn't matter. At most 1, I mean the height difference. So we need to do the 3 rotation, this, yeah, for rebalancing the height. We can discuss later about this. Okay. So we have most operation in BSD, binary search tree is find particular element, then max to find the maximum value, min, minimum, insert, delete, etc. Yeah, etc. So need the time complexity, yeah, big OT, where T is BSD height. This height. This is become only 1. This, yeah, the height. It can be faster. It can be faster. So if big OT height, so for instance, this already, yeah. For instance, log n, yeah, because it's like faster. Log n. Okay. So the faster mean, for instance, big O log n. Yeah, we also discussed that for sorting, for instance, become the test case, yeah, to check the lower bound, yeah, log n. Okay. Then big O n for the skewed binary tree, where n is the number of nodes. See already that if skew like this, yeah, skew, it's totally skew, or like this, first become n. Yeah. If the tree's height can be kept to big O log n, somehow the tree height can be kept to big O log n, yeah, after insertion and deletion, then upper bound can be maintained at big O log n for this operation, where n is the number of nodes. And that's why what is the enhancement, yeah, and advancement of a binary search tree that Georgi Adelson Felsky and Yevgeny Landis, that for the worst case, for such insert and delete operation, they're able to get time complexity big O log n instead of big O n. This is why it's amazing. It's very fast. The height of FL3 is always big O log n. This fortunately, because we keep try to rebalance anytime you do insertion and deletion, and then after you did insertion or deletion, and then you check, and actually the height difference between the left and right branches then not at most one anymore, yeah, maybe two or three or whatever, yeah, and then need to rebalance. Yeah. The thing is, it always keep rebalance in order to keep the property of EVL upheld, because when you keep this property upheld, it means upper bound of all operation is big O log n. This is the only purpose for EVL is to make efficient, yeah, for all of operation. Yeah, this set, insert, and delete very fast. Comparing to worst case, we can, well, of course, in average, when binary set is already okay. Yeah. But if skew one, and then okay, you got will jeopardize, yeah, your process. Okay. So this is the example, for FL3 and not FL3. Okay. So see the particle 5, yeah, we discussed already. Because we thought children, it means different at most one. Okay, about 6. This is 0, yeah. If I said right minus L left, then this 1 mean 6 actually minus 1, yeah. So still okay, yeah, minus 1. Typical minus 1. 12, you know the case, if only 1, yeah. Oh, but 9, case of 9. So I have 1 here, height, yeah. Then 1, 2, yeah, 2. So 1 minus 2 for the node 9, it means minus 1, yeah, still okay. 18, you know already that is okay. Oh, but this 19, the subtree rooted in 19. So this is 0, yeah, minus 0 and then 1, yeah. 0 minus 1. Yeah. So it means minus 1, yeah, for the node 19 is minus 1. How about the whole 3 rooted in 13? So this is what is the height until 18? It means 2, yeah, and then this 1, 2, 3. So 3. So 2, yeah, minus 3 equal to minus 1. So minus 1 in here. So it's also okay. Yeah. This is not FL3. Yeah. You can check. Yeah, okay, 13 okay. Pass. Rooted in 5 also okay. Pass. Rooted in 6, no? Check. Not pass. Yeah. This is 1. Oh, still pass this. Yeah. 1. And then this 1 and 2. It means in 6, it is minus 1. Still okay. 12 also okay, means 0. Yeah. From 9, yeah, 1. Okay, this case, yeah. This is 1, yeah, minus how many? 1, 2, 3, minus 3. So in sub 3 rooted in 9, the height difference become minus 2. So this is minus 2, it means FEL 3 property. Because to be at most 1, yeah, at most 1. Okay, at most 1. It means should be, can be plus 1 or minus 1, yeah, or plus 1. Yeah. This plus 1 or minus 1. It is minus 2, it means it is not correct. Yeah. This is okay. Difference is 0. This is 0, minus 1, minus 1. This is 2, yeah, minus how much? 1, 2, 3, 4, yeah, 4. Mean minus 2 also. Okay, but it's not FEL3. Okay, guys, it's so easy to understand, yeah, this. Okay, we want to discuss about insertion in binary search tree, the standard one. Instead of new element of value in standard BST as below. New element always be inserted as a leaf node. Leaf node. So I mean in the fringe of any particular tree. Yeah. So this is fringe. Fringe this, yeah, this fringe this also. Yeah, if you put new one, if then you put here also this fringe. Yeah. Okay. Inserted as a leaf node. Then we have to find the place for the inserted node started from the root until the leaf node found. So it means you go from root here, yeah, and then going down, yeah, going down to find the proper place. Once the leaf node found, then a new node will be added as a child of that leaf node. So instead, okay, you have this 120 and so on, and insert 50. Okay, you started from root, yeah, 100, then 50. Because 50 is less than 100, so we go to the left, yeah. Get to 20, because 50 is larger than 20, so go to the right. Then you get 30. And see 30 is, in 30, I mean 50 less than, greater than 30. So it was 100. 100 is, I mean that 50 is less than 100, mean go to the left, go to 20. 50 is larger than or greater than 20, go to the right. You got 30 and 50 greater than 30, it means go to the right. Yeah, go to the right here. So you are here. Yeah. Just remember the property of PST element left, less than element root, and less element right. Yeah, that root is 100. Yeah. So that element left, for instance, 20, yeah, less than 100. And the element of right, 120, I mean greater than 100. Yeah. So it is easy to understand. Okay. And then a bit complicated for FEL3. Yeah, for that insertion procedure. Yeah. To maintain the FEL3 condition after insertion, the aforementioned standard PST insertion needs to be modified, yeah, to regain its balance. Because you can imagine like this is not balanced anymore. Yeah, this is balance. Yeah, 0. This is 0. It is only minus 1. Yeah. That's good. This is 0. It is minus 1. Yeah. It is 1. Yeah, plus 1 because 2 minus 1. And then this is okay. This is 0. Now become 1. Yeah, 1 minus 3 equal to minus 2. Yeah. Right. Minus 2, it is imbalance, yeah, because at most 1. Yeah, the difference. Either plus 1 or minus 1. Two basic operations for PST rebalancing without breaching the PST property. This, yeah. So you have left rotation and right rotation. Okay, what is the left and right rotation? Assume, yeah, P1, P2, and P3 are the branches of the tree with the root Y. Left picture. So if rooted in Y, this, and rooted in X, this, X. Yeah. This P1, P2, P3 is like any node, yeah, can be empty, empty node, yeah, only one, or many. This, I have three in here. So this all is represented by this triangle, yeah, triangle. So if you want to do right rotation, it means you lift up X, you kick X up, and you kick Y down. Yeah, this is a right rotation. That's why now X become the root and Y going down. Yeah. This. Likewise, if you have something like this, yeah, then you wanna kick Y up, you promoted Y, then kicks X down. Yeah, you push down X. Yeah. So this left rotation is. So now Y become the root, yeah, and X going down there. If you wanna check the elements of that tree above, still following the rule, yeah. P1 less than X, correct, yeah, this. Okay, P1 less than X, correct. Oh, but X less than P2, X less than P2, it is, yeah, this, yeah, this X less P2. X less than P2, it is, yeah, this, okay. But P2 less than Y, it is obvious, yeah, yeah, less than Y. Okay, P2 less than Y also correct in here. So, but Y less than P3, it is obvious in here, and also obvious in here. So it's still following the BST property compliant, yeah, left and right rotation. So how to say the shape of tree changes, yeah, but the property still upheld, yeah, so it's okay. Okay, this is the procedure of AVL insertion, yeah. So the node will be inserted is S, okay. Do the standard BST insertion for S. Just you do like this. Like this. Yeah. 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 This. This is standard. Yeah. Okay. Then starting from S, go up and find the first imbalance node. So if I have S here, then you go up, yeah, until you get first imbalance node and name it Z. Assume that Z is the first imbalance node. And then Y is the child of Z which came from the path of S to Z. So I have this is Y. It's the child of Z. Yeah. And X is the grandchild of Z, which came from the path of S to C. So I have this X here. It means child of Y. It means the grandchild of Z. Okay. And then you do rebalance the tree by any proper rotation. Yeah. On the branch is rooted in Z. Rooted in Z. So rooted in Z. You need to do rebalance. Because there are four possible cases, so it means X, Y, and Z can be arranged in four positions like this. First one, so this the first one. Y if left branch of Z and X is left branch of Y. So something like this. This first case here, this Z here, and then Y is left branch of Z, and X is left branch of Y. Yeah, this X. So this we call it LL, left case. Okay, the second one, no, y is left brand of z and x is right brand of y. So I have z here, and then this left, yeah, y, and then right. So x is right brand of y. Yeah, you can see, yeah, this is L like this, L L. This is left and then R. So it means also the same L R case. Yeah. Left right case. This is left right case. This is L L case. Okay. And then the third case is when y is right brand of z and x is right brand of y. This right case. See also z, and then you have y here, right branch, and then x also right branch of y. So it means you got RR, yeah? Right case. Okay. This. Then last case when y is right branch of z and x is left branch of y. So you see here, yeah, right here, yeah, that y, and then it is left x left branch of y. This R L. Yeah, it is ref, right, left case. Okay. Yeah. Okay. How about left case? LL. So assume P1, P2, P3, and P4 are the three branches as usual. So if you have left, right, left, it is easy. Just do uh, right rotation on Z. So I mean you kick Y up, yeah, and then kick Z down. And then instead of Z as root, now you have Y as a root. Yeah. So this new tree rooted in Y now. So it was Z minus 2, yeah. The head difference now become 0. Balance, okay. Right rotation, you just kick Y up and Z down. It was rooted in Z, it's like right rotation Z, and then become rooted in Y, okay. This is LL case. How about left right case? So you have left first this, and then you have right case. If you have LR case, it is also easy. You need to strengthening because you have LR, yeah. See that L. So you need strengthening to the left first. See, this is L and L. Something like this, yeah. You have strengthening to L. Yeah, you have to do this left rotation first. This, yeah, left rotation this. Okay, so it means X become the root, yeah, of the shape sub tree, yeah, this sub tree, and then you kick Y down. So you kick X up and Y down. So you are strengthening, yeah, strengthening to the left first, yeah, and then go right rotation afterward. X up and Z down. Yeah. That means you will get the new tree rooted in X. It was also minus 2. Yeah. 1 minus 3, I mean minus 2, becomes 0, the height difference. Okay. This is our case. Hmm. How about RR case? It is the mirror of LL case. Yeah? Mirror of LL case. It's also not typical. RR case. Yeah? This RR case. Similar P1, P2, P3, and P4 are three branches. So if you have right and right, right and right, so just do left rotation. I mean you kick Y up, right, and then Z down. So now you have the new 3 rooted in y. It was, that is 3 minus 1, yeah. So plus 2 now becomes 0. That height difference. This is RR case. For right left case, RL. So this the mirror of LR. LR, mirror of MLR. Yeah, so this is not typical. Yeah? So you have right left case. Yeah. So right first and then left. Easy. You need to strengthening to the right first. Yeah, this. So this is strengthening this. Mean you kick Y down, yeah, and kick X up. Then after you have this strengthening to the right, yeah, then you do left rotation by now kick Y up and X down. Then you have a new 3 rotate in X. Yeah. So it is 3 minus 1. Yeah, I mean plus 2 becomes 0. The height difference. Okay. That's the example. Okay. Okay, one by one. Yeah. So in this picture, it is references height minus or subtracted by left one. So one by one. Yeah. Okay. In this case, see guys. Yeah. Right minus left. 0 minus 0. Of course 0. This also. Yeah. Not 6. Value 6. 0 minus 0. For this 1. Yeah. Right 1. This. Yeah. The height, and then left also 1. 1 minus 1, 0, yeah. This, 0. Okay, so all of the leaves, you know, yeah, this all 0 should be, because there is no children. Okay, how about this 15? So you have 1, height this, and minus 0, yeah. And 1 minus 0. Of course, plus 1. Okay, this plus 1. Okay, how about this 10? Okay, this is 1 minus 1, 2, yeah. The height, I mean the longest one. So 1 minus 2 equal to minus 1. How about this 13 one? You have 1, 2. Yeah, I mean 2. Minus, which one the longest? 1, 2, 3. Mean minus 1. This. Okay, correct, yeah. And then insert note with value 14. Yeah. You start from 13. Yeah, the root. Of course, root. Because 14 is larger than 13, you go right, yeah. Then you got 15. Because 14 is less than 15, you go left. And so this is your place now. Okay. Okay. Then check once again about the 3 and still balance, yeah. 0, 0, 0. Yeah. It was plus 1, yeah. Because you got the new left branch become 0. 1 minus 1. Okay, good. So it is balance. Okay, another example. Yeah. So I have this. It is a case of this. Yeah. And then insert note with value 3. Okay. From root, yeah. Of course, starting from root 13. Okay. It is 3. Of course, go to the left. Then 10. Go to the left. 5. Go to the left. 4. Go to the left. Okay. And then this is your place. So it was, check the balance, it is okay. All balance, maximum plus 1 or minus 1. Maximum. So and then you need to count also, yeah, the height different. And then actually you got this balance here. Yeah, this is 1 minus 3, yeah, equal to minus 2. This balance, it will also become imbalance also this, yeah. And the root become -2 instead of -1. Okay. Okay, and you can check guys, yeah, because see that you go for left, yeah. This is left, right? This is left, yeah, left, and then left, yeah. LL. If L need what? Right rotation only, right rotation. So easy then, yeah. So the first imbalance, yeah, from this is S, right? Then you go, then it is Z, yeah? The first imbalance. You can check, yeah, this is left, right? Left. It means need right rotation. It means you have to kick 5 up, yeah, and push 10 down, yeah. Then you will get this particular one, right? Okay. Then going down, yeah. Of course, then 8 and 11 become 10 children. Then once again, you need to count the height difference. They're not okay, yeah. From -2 become 0 here. Then become this 2, yeah, -3, of course, become -1. So this also okay. 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 So then as pivot, yeah, pivot. Okay, this is another case. It is not the same like in this case, guys. It's not the same. So I have this, yeah. This is balance, yeah, maximum at most 1. Doesn't matter +1 or -1. Now you insert 45. Okay, from starting from the root, yeah, 30. Of course, 45 is greater than 30. Go right. 35. Go right. 40. Go right. Okay, 45 in here. And then need to recalculate the height difference and become imbalance, yeah, because it is 3, yeah, 1, 2, 3, the height -1, this become +2, okay. So it seems like this, yeah. This is S here, yeah, 45, and then go up, yeah, until the first imbalance. What is Z? And you can see this is what? Right, yeah, right, and there's also right branch, yeah, right branch of Z and right branch of, let's say this is Y, and then this is X here, yeah. RR case, RR case. Yeah. It is red ribbon. If you guys watch the cartoon Red Ribbon, RR. RR easy. Use left rotate, yeah, left rotation. Yeah. It means you need to kick 40 up, right? Yeah. And then, oh, sorry, this is a value 30, yeah. So need to kick 35 up, yeah, and 30 down. Okay, so 30 down, become here 30, and 30 up, 35 here. Yeah. Then recalculate the height difference, and then okay. Yeah. Instead of +2, because now is 2, yeah, -2, equal to 0. And this. Okay. You know that red ribbon, because it is when I still in undergrad like you. Red ribbon. Soldier. It is in Dragon Ball. Yeah, in Dragon Ball, yeah. This RR, this I remember it. Well, it is also I really have also good time in my young age, yeah, like you guys. Yeah. Okay, so it's good, yeah, that when it is RR case, yeah, right case, and then just do left rotation, yeah, and then voila, you got the balance again. You regain the balance. Okay, another case. It is different case also, yeah. So I have this all balance, and then insert node 7. Nah, make it bigger. Starting from the root, yeah, 13. Of course, you need to go left because 7 less than 13. Yeah. Okay, to the 10. Okay, go to the 5 because 7 already greater than 5. You go to the right, yeah, and 6. Okay, no, it is your position is there, yeah. Okay, so remember it is S, yeah, here, and then you go there, yeah, then you go there to get this 10, yeah, this 10. For the first imbalance, this first imbalance, this right. It means from the Z 10, yeah, Z, you have left and then right. What they mean? They mean all error case, yeah, all error case, left, right case. How to do? You have L first. Yeah, mean to do strengthening, yeah. If you have this, you need to strengthening this, guys. To have this, yeah. And then you can do right rotation afterward. Yeah. So need to left rotation first, and then go right rotation. Okay. That's why after you insert 7 and then you got imbalance in node 10, I mean the value 10 plus 2, minus 2 there, yeah. Then you need to strengthening. It means you kick 6 up and 5 down. Yeah. That's why now become 6 become the root. And then after that, have a right rotation in 10. When you kick 6 up and then 10 down, yeah. 6 up and 10 down here. Then all balance, yeah. It instead of minus 2 in 10, it becomes 0 in 6. Okay, good. Yeah. Okay. Next one, next example. I have this. And then insert 15, starting from the root, 5. If it is 15, mean go to the right. Yeah, okay, 7. 15 greater than 7, go to the right, 9. Okay. 15 greater than 9, go to the right. And then 16. It is 16. It is 16. Of course, 16, 15, go to the left here because 15 already less than 16. Okay, then, okay, this is 15 here. This is your proper place, 15 here. And see, as this, yeah. Then you go here, and then you go here. The first imbalance is 9, yeah, this plus 2. S, and then Z is in 9. Yeah. It means it is left here, left brand, and then this right. Okay. Oh, sorry, this right. So this is right. I should remind me. This is right. Right branch, and then left branch. I mean L error case, yeah. L error case. L error case. RL case, yeah. RL case. What I said and what I read sometimes different. Yeah. RL case. Okay. You have R, this RL or RR. It means you need to strengthening, yeah. If you get case like this, you need to strengthening right first, yeah. Right rotation, and then you kick, yeah, with left rotation, yeah. This, and then this. Yeah, this is RL case, ref left case, right left case, right R RL case. Yeah, you need to strengthening to be right. Yeah, this is right. Then kick to be to get this is strengthening by what? Right rotation. Yeah, rotation. Then you kick by left rotation. Left rotation. And you can check, yeah. Okay, this RL and then 9 it become the first imbalance ancestor of 15. Yeah. Then you need to do right rotation to strengthening, strengthening this. It means you kick 16 down and kick 15 up. This. Okay, and the strengthening RR, RR branch. Then you go for left rotation by 9 as pivot, because this also pivot of 9, This is imbalance. Okay. Yeah. So it means 9, this, then become 9 become going down, You push 9 down and 15 up, this 15 up. Then 9 down, and this. Yeah. This is a left rotation, 9 as pivot here. Then you can check, recalculate the height difference, and instead of plus 2, in 9 become plus 1 in 7. No, actually this becomes 0 in 15 here. So you can become balanced. Okay. So it's easy to understand, that what kind of case this LL, RR, or RL, or LR. Then what kind of treatment to make it balance? I mean rebalance again. Rebalance. Okay, so now the implementation of that insertion in EVL. First, do the BST standard insertion. Just like what we do. This just insert, for instance, this 15, and then rebalance. The current node should be any ancestor of the new inserted node. I mean the one that we proceed now. So for instance, you have this 15, and then the current node. It means the one who the first imbalance. I mean this become 9, right? Because it's plus 2, plus 2. Okay, plus 2 is the first imbalance. So update the height of the current node. Of course, this become plus 2.9. So should be any ancestor of the new inserted node. And then get the balance factor, the height of left branch minus that of right branch. And then, because when I and my team when I was in UK, for teaching that software workshop in Java programming. So we already do this. Instead of the book should be this. For instance, this -1. It is right. I mean 0, and then this height is 1. So 0 minus 1 become -1. So it means this is right branch height minus left. In this picture. But in our program, that's by the algorithm, this L minus R. So sorry for this. Just be consistent, because we already did this. So in program we need to do all left minus R. But in the book, because when I find the example of the trees, this they already did right R minus L. So let it be. I mean, if you do R minus L, then every node need to do exactly the same formula for calculation. So that's why you get this, you get this, and you get this. Okay. Okay. So if okay, in this case, remember, it is L minus R. So if the balance factor greater than one, then the current node is imbalanced. And we have LL, or left-right case. LL or left-right cases. So this LL or LR. To check whether it is left case or not, compare the new element value of inserted node with the element value of the left branch root. Which one? This. So this is LL. It should be here, This. So if you inserted this 7, yeah, then left branch, this. See, this is LR, yeah, LR. If it is LL, is there any LL we have here? This, yeah. This is RL. Is there anything LL? Value 14. This RL, this, yeah, RL. What is that? This is LL, yeah. This is LL. Yeah. So this, I just compare for this, guys. Yeah, so easy. Which one of the left branch of the root? Yeah. Okay. So if this is LL like this, if LR, where is LR? There's LR. Yeah, this LR like this, yeah, LR. Okay. So it's easy to compare, yeah. This it is LL or LR, just compare, yeah, the new element value. Yeah. You can check, for instance, if it is LR case, yeah, this is become what? The first imbalance, yeah. This is in 10, yeah, -2, yeah, in 10 LR case. And then for LL case, in this case, I need to compare the inserted, what is this? Value 3, yeah, here. Yeah. I need to compare for the left one. Yeah. This -2 in 10, yeah. Yeah. Okay. You can check this. Yeah. Okay. So this is yeah, -2. This is, and then you just kick, yeah. Then you get the balance. This for LL case, yeah. LR, this, yeah. LR, yeah, yeah. So we have, this is -2, but this is +1, yeah. +1. Yeah. Then -2. So it means what? If there is a changing of sign, yeah, this is, yeah. It was +1, then become minus. So from minus to, from plus to minus, yeah. So it is become what is LR, yeah. LR. If it is LL, yeah, this is this, yeah, minus, yeah, minus, minus 1, right? Minus, and then become -2. So there is no changing, yeah, in the sign. It means it is LL. Yeah. This is LL, yeah. -1 and -2 for the first imbalance. Yeah. If LR, there is LR here. Now you have plus and then minus. That's why it is actually easy to see, guys. Yeah. If um, plus, it means you go right. Yeah. In this case, I mean, in this particular case, it's a bit typical because we did left minus R and here right minus L. Yeah. But anyway, if it is constant, okay. So if it is minus, it means you have left more. And if it is plus, right? If you go right, I mean right more, right? It's very easy to check if it is LL or LL or LR. Yeah. Why this minus minus? It means nothing changed. Mean LL. Yeah. If it is, if you see from right, from root, it means minus and then plus. Yeah, it means LR. Yeah. It means minus and then plus. It is LR. If it is LL, it means from minus here. Yeah. Minus here. minus here, then minus here. So minus to minus. So LL. Okay. But if you, because we have left mean right, yeah, you just do it inversely, yeah, so easy. Okay. Okay, this is for the balance factor greater than 1. If balance factor less than -1, so I mean when some greater than -1, it means -2. So then the current node is imbalance, and we have RR, yeah? Right, or right-left case, or right-left case. And again, to check whether it is right case or not, compare the new element value of inserted node with the element value of right branch node. With an RR this, yeah. So RR, it means you have, in this case, yeah, you have plus and then minus, right? Isn't it? Yes, it is, yeah. Plus, where is that plus? Yeah, this, yeah, this plus. See, this is plus. Right, plus, yeah. And then should be maybe changing, should be, if zero also can be changed, yeah. Plus become zero, also change this, yeah. It's actually zero here. This is how much this is. Minus, yeah. Oh yeah, it correct. Should be, oh yeah, correct. Plus to minus, yeah, because it is zero, yeah, minus one. So it is -1. This, yeah. Okay, correct. Yeah, plus two and then -1, yeah. So RL, if RL, it means plus, then two minus. Yeah. If RR, where is RR? Where is RR, guys? Here, yeah. Yeah. RR, it means plus plus, yeah, isn't it? It is, yeah. Yeah, it is, yeah. So 45 is here, yeah. You have plus two and then plus one. Yeah? So RR means from plus to plus. Yeah. Correct, correct. Yeah. Okay. Okay, this, yeah. Okay. So it's easy to check, yeah, whether it is. Okay, so this is insertion in EVL, yeah, AVL. How about deletion? No, we talk about deletion in binary search tree first, and standard binary search tree. So you have three case possibilities, yeah, in deletion. Three case possibilities of an element value in standard BSD are below, yeah. So the node will be deleted if deleted is a leaf node, yeah, because only deletion, yeah, deletion. So for instance, I have a tree like this, and then the one that I want to delete is leaf node, here, leaf node. Even I don't have a children in here, right? Even this leaf node already. If I have no children, just delete it, yeah. Just delete that node from the tree, easy. Okay, just delete this. Okay, and continue. Yeah, that is the first case. Okay, the second case, if the node will be deleted, only has one child. So I want to delete 30 and I have one child 40. So I delete 30, how to do? Copy the child to the node, I mean 40, I copy in here, become 40 here, right? And then delete the child, yeah, delete the child. Okay, so it was here, yeah. So copy 14 here, then delete the child. Okay, easy. This number, this is the case, the second case. The third case, the node will be deleted has two children because I have 50 want to delete and then I have 40 and 70. I have two children. So you have to find the next the next means successor. You have to find the next node or successor node from the node will be deleted by using in order traversing, and we call it in order successor. So if you want to delete 50, it means you go right, yeah, successor right. And you have to find the minimum right branch. You go to the right, yeah, and then which one minimum? Of course, 60, yeah, the minimum one is. It is, we call it in order successor. Then copy in order successor to the node will be deleted. So 60, I will copy to 50. Come 60 here. Yeah, and then delete in order successor this. Okay, yeah, so 60 I copy here and then I delete. Okay. Another alternative, or alternatively, the previous predecessor node of the node will be deleted by using in order traversing, and we call it in order predecessor. Can also be used as a copy before node deletion, but you have to find max left branch. So for instance, this case, yeah. For instance, this case, actually I have here 45, guys, 45 here. Yeah. So 45 here. So 50 I wanted to delete, yeah. So I want to find in order predecessor. So it means I have to go to the left, yeah. Because this predecessor, before predecessor, yeah. And then to find maximum left branch, maximum. This maximum. For instance, I also have actually 40 and here, yeah, pizza, okay, let's say 30 in here, 30 in here. Yeah, 13 here. I go to the left, yeah, go to the left, and have, of course, many predecessors of 50, yeah, 40, 30, and 45. If you want to perform deletion in PSD by in order predecessor, you have to find the maximum value of the left branch. Okay. In order predecessor is 30 and 45, so maximum is 45 here. Yeah. So this maximum of left. This is minimum, yeah, minimum of right, minimum of right. In order successor, it is maximum of left. I mean, in order predecessor. And then copy, yeah, for 45 to that one to want to delete, yeah. So copy 45 here, yeah, and then delete, yeah, that 45 one. Yeah, like this. Okay, so this two things, yeah. There is two ways to do deletion in BST. Yeah, so there is a node in order successor can be used if the exist children in the right branch. In this case, in order successor can be obtained by finding the minimum value of children, yeah, in the right branch. I mean, right branch for them from the node will be deleted. Once again, if it is predecessor, should be maximum of left, yeah, maximum of left. It is predecessor. Predecessor. Okay. What is actually in order successor in BSD? Yeah? It is a node. In order successor of a node is the next or successor of node, which can be obtained by in order traversing. You know, the successor has a null value for the last node in order traversing. A null value for the last node. In BSD, in order successor from a given input node defined as node with the least value, which is greater than the value of input node. Sometimes it is important to find in order successor in order tree. I just see the example. Okay, successor of 8 should be go to the right, yeah. That is 10. Yeah, the list of 10, 12, and 14, of course, 10. How about 10? Go to the right. To the right. Of course, only 12. Yeah? How about 14? You go to the right. Then only 20. Yeah, yeah 20. Okay. Okay, now after we discuss about deletion in standard binary search tree, how about deletion in FL3? The thing is only we need to maintain, right? The maintain of the property. Yeah. So maintain FL3 condition after deletion, the aforementioned standard basic deletion need to be modified, yeah, just like insertion. So basically the same, yeah, left rotation and right rotation, yeah, with the property of this. Okay. Yeah, we also already discussed about this, yeah. So left and right rotation, yeah. Okay. Right rotation here and left rotation there. Okay, how to do? The same, similar with that insertion, that node will be deleted is S. Then do the standard basic deletion for S. And then similar, so starting from S, go up to find the first imbalance node. Assume it is Z. And the difference is when the division of Y and X, yeah. If Y and X in insertion, only the child, yeah. But this is, Y is the highest child brand. It is about height. Yeah, bisa. So it is the highest child brand of G. So this is the highest. And X is the highest child brand of Y. This X. Not just child, but the highest. I mean, how to say, the not whose highest, how to say, the height is the, how to say, the number one. Yeah, I mean the height of that particular node has the tallest one. It is the tallest one, the highest child branch have height the most. Okay, so I have noticed the definition of X and Y are different from X and Y in the previous EVL insertion. And this is the, well, it's not like this guy. So I have this, yeah. And then if I have, for instance, this. So this I only have height what? 1, yeah. This I have 2. So the height it means this 2. Yeah. Okay. So I put this. Wait a minute. Okay. Wait. Where is that? My. Sorry that Kastin ya. Most WhatsApp me. Mhm. Terima kasih. Thank you. Yeah. So yeah, just similar with insertion, guys. Yeah, the deletion only instead of child, but it is you choose the highest child branch. Yeah? Just like I said, this it is only 1. It is 2. It means you choose this. Yeah, this. How to say this? I mean, you will see that which one. Yeah. So you will have that height, the balance that This where is that deletion? Yeah, the balance, the height factor. Yeah, the height factor. We'll see the example. The example. Yeah, the example. Yeah. So this I have. Yeah, this is -2, -1. This, yeah. This. Then for instance, I have another. Uh, this is, yeah, 1, -2, -1. Yeah. And then for instance, I have something like this. What is the highest 3? For instance, I have this. Then for instance, I have another one like this, guys. Wait. Yeah. So this is 1 minus 3, yeah. 1, 2, 3. So it means this is -2. Yeah. So if I have -1 and -2, and it is all the child of this, yeah, in Z. Yeah, so not the child of Z. There's dot on this, yeah. So the highest, it means you need to choose this -2. It doesn't matter really -2 or plus. Let's say if it is by that our program, yeah, it means +2 and +1, yeah, because left minus right in our algorithm, yeah. It means +2 and then +1. Yeah. So it means you choose the highest one, this highest child. This, it means we will choose this, yeah, +2, the height factor, yeah, instead of +1. So that's the explanation of this second point, yeah, that assume that Z is the first imbalance node, Y is the highest child branch of Z, and X is the highest child branch of Y. Yeah, that X is the highest child branch of Y. Okay. So X and Y, yeah, this X and Y. Okay, this. Then rebalance is the same, yeah. The rebalance is, I think we don't need to discuss about this anymore because it's similar with insertion. Okay. As in eval insertion, each cases will be described in the following. Yeah. But the difference is this. So just pay attention for deletion. Not as in insertion, rebalance on node Z does not rebalance a whole EVL tree. After rebalancing Z, most probably the ancestor of Z should also be rebalanced. So not just stop in Z, yeah, but you have to go up. Not just okay, you have S here and then Z. But you have to go up until, let's say, maybe even until that top one, yeah, top root here, top root here, yeah, top root here. Okay. Okay, so that LL case and so on, I think we don't need to discuss anymore. Yeah, I think you know already about this. It's the LL case, yeah. So LL, left, left. Need to do right rotation. Yeah, right rotation this. Yeah. And then left, right, you have left and then right. You need to strengthening first, yeah. Strengthening LL, yeah. And then you do that right rotation. Yeah. Right rotation. Okay. If right case, yeah, R, 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 R is easy. You do left rotation. Yeah, left rotation. Okay. If it is right left case, yeah, see that it is right R and then left. You need to strengthening first, yeah, by right rotation, and then you do after strengthening this, you do left rotation, yeah, L rotation. Okay. This is not as in eval insertion. In deletion, after we did rotation on Z, then we might do the rotation on the ancestor of Z. That's why we have to continue our traversing up to the top root, top one. Okay, one example, yeah. Example of deletion. Okay, deletion. Okay, should be okay. To make all can be seen. Okay, I have small this, yeah. Plus. Okay. Note whose value 32 will be deleted. Okay. So this yeah need to be deleted. This 32. 32 need to be deleted. Note with value 32 is being deleted. After deleting 32, then go up and find the first imbalance node, i.e. 44. This 44. Because you see the height, yeah, the height factor is 4, right? Remember, maximum is 1, yeah. Maximum plus 1 or minus 1. Okay. We mark 44 by Z. Yeah, this is Z. This is Z. Okay. Then Z highest child branch as Y. Because the highest after Z is 3, right? So this is Y. This is Y. Okay. And then this is this is Y. What is this? Y, yeah. And then Y's highest child branch as X. Actually, we have two, guys. Yeah. Okay, Y here, and then you have children. This 50 and 78, where both of them got 2 and 2 as a height factor. Yeah. If you have two, which one the highest one? Because 2 and 2 the same, so you are just choose arbitrarily which one, and then we choose 78. Okay, just it is arbitrarily. Okay, you also can choose 50, yeah, because 2 and 2 the same. So you have what? RR, yeah, this R, this is R. Yeah, this one RR. So the left rotation will be done. Just left rotation. Yeah. Okay. Okay. This so and then you do rotation. Mean left rotation. It means you this yeah. This yeah. Okay. So you will kick up 62, yeah, and push down 44, yeah. So 44 become down here, and then 62 up, yeah. Okay. Now remember, this is still F3. This is 2. Yeah, this is 4. Yeah. So it's still not balanced. Yeah. So you have to go up, yeah, again. So you need to rebalance until all upheld the property, yeah, of that FEL3. Need to rebalance. Okay. And then about the programming, because it was we have a team teaching when I was in UK. 6 years I teach Java, Java, this software workshop about Java programming. So basically, it is we have list, just like linked list. You have list, how to find if it is list empty, and how to get the head. What is the head of the list? What is the tail of the list? Yeah, and then whether two lists equal, yeah, and so on. So this is the list. Then list op, I mean the operation of list. Whether you wanna find what is the last of the list, yeah? And then you wanna add up any element to the end of the list. Yeah. You can append any element in that list. You need to reverse list. For instance, 2, 3, 4 become 4, 3, 2. You know? What is the maximum in the list element, yeah, and so on. Then I have a tree. Yeah, it is binary search tree actually, left and right. You can get What is the value? If you go to the left, go to the right, what is that element? Yeah, and so on. And then also the operation of tree, whether you want to get the height of the tree, if you want to traverse in order, this. Then for the search tree, you can find a particular element in a tree, and then insert this insertion in a binary search tree. Yeah, so easy. Okay. Then we have FL3 here. Yeah, it's the same like what I copied here. So it is the extension of the tree. I mean, actually, this is a PST, binary search tree. So you can create empty tree. Yeah, it means it is really empty. This why the empty is true, value 0, and left to right null, height is 0. Or you want to create only one element. So it means the height is 1. Yeah. And left and right have uh, empty branch, the value, and empty become false here. Yeah. And then I have one, I adapt the property of height to make it very efficient, calculated, and then the height determined by this 1 plus the maximum of left get height and right get height. And this. So that's the simple one. Yeah. Let's see, of course, if then we make this become our midterm for question in midterm, the assignment, maybe I will, of course, I will give you the proper code. Yeah. If you want to continue in Java programming, because as usual, many people, students also, but can I do in C or Python or C#? Of course, you can. Yeah. And for me, once you are able, you are mastering one programming language, then easy to move to another programming language. Yeah, just because the logic is the same. Yeah. Okay. Then we also have some exercise. Yeah. At the time. Yeah. For instance, in the list, if you wanna do power function power, it means m power n. Yeah, for instance, 2 power 3 equal to 8. Yeah. And because we also deal with the divide and conquer approach, it means recursive. If it is power, and then you need to call power. Fast power, just to make sure that you compute m to the power of n in big O log n time. And use this exponentiation by squaring instead of divide by 2 in this very, how to say, this time consume. Yeah, we just shift it by bitwise operator by 1. And then if modulus also is very, very time consuming, so just use that bitwise operator n, yeah, and so on. For instance, if we get all, just use minus, yeah, something like this. So what we are doing this, it is of course focus on programming, but the thing is, I think even though we discuss about algorithm, if we don't discuss at all about programming, also it is wrong. That's why okay, we also do fine. But I believe in you because you guys already passed data structure and so on. So this kind of programming thing, yeah, I think no need to discuss too long about it. For instance, to find any element in list like this, yeah. Okay, and then okay, I also try some here. Yeah, for instance, if you wanna check, for instance, 2 power 4, yeah, you can also run this. Yeah. See, because usually I also ask my student to record the time you are starting and the end of the programs, which one is faster, and then to compare and so on. Yeah. Okay, I think it's no problem, guys. Yeah, about the programming. Yeah. At that time, I use Java. Yeah, but of course, for the competitive programming, usually use C or C++. Yeah, it was very, very fast. But of course, we also need to find the efficient one in program. But above all, I think it's still better. Yeah, that we understand the algorithm first. Yeah, then understanding the essence and the philosophy algorithm. Yeah. Programming also, of course, important, but I think the the story behind the algorithm and so on. I think I was going to be understand first. Okay, that's all. I don't want to take more time, guys. Yeah, I need to stop sharing now. So as usual, please make a dua. Yeah, may Allah, our good Lord, lift up this pandemic, this coronavirus as soon as possible. Yeah, and also this vaccination smoothly going through. I got one. Yeah, I got one jab, guys. But the last 2 weeks. Yeah, and then inshallah the second jab after Lebaran. I also wish that you also will get as soon as possible, and then we will get back our normal life. Yeah, I really miss our class and every activities. Okay, that's all, guys. Yeah, have a nice weekend. Inshallah, we'll meet for next lecture next week. Yeah. Okay, thank you, guys. Have a nice day. Have a nice weekend. Assalamualaikum. See you, guys. Thank you.
Waalaikumsalam. Thank you very much, sir.